So seawater density is important because dense water tends to sink, and this is what helps drive ocean currents and ocean circulation. So at the poles, it's cold, it tends to be a little bit more salty, the water is dense. The water sinks down and it starts to move down towards the equator. When it gets to the equator, it heats up and it rises again. And so you can see these red arrows represent warm, less dense water, and the blue arrows represent cool, more dense water. And so these create big ocean circulation patterns called gyres. This, for example, is called the North Pacific Gyre, which is important because we're almost right in the middle of it. And it happens to be a really important place for us to be in order to understand how these currents move nutrients, move oxygen, and influence marine habitats, both in the shallow waters and in the depths. So we'll come back to currents, but let's talk about some of the other chemical properties of water. So we've talked about salinity, right? What about gases? What different gases are dissolved in water? The majority of gases are oxygen, carbon dioxide, and nitrogen. Interestingly enough, oxygen is not very soluble in water, which is why a lot of marine organisms have respiratory tissues that have lots and lots of surface area so they can maximize contact with the water to maximize gas exchange. In the water, there's about 4 to 6 mils per liter of oxygen dissolved. In the air, it's 210 mils per liter, or 21%. So it's much more, much easier to get oxygen from the air than it is from water. Contrary, carbon dioxide is very soluble in water. It's about 800 milliliters per liter in water compared to about a thousandth of a milliliter per liter in air. And here's an example of what I mean by lots and lots of surface area for respiratory structures. You can see the gills look like feathers, and that's all that surface area. So let's talk about some other physical characteristics, mainly transparency and light penetration and pressure, as well as water movement. So transparency is just the ability of sunlight to penetrate through the depths of the ocean. This is really important for photosynthetic organisms. As you might imagine, photosynthetic organisms can't live in the deep ocean because there's no light down there. So they're limited to the surface waters. And they also, because of photosynthesis, help contribute to oxygen levels. As a matter of fact, not just to oxygen levels in the ocean, but also in the air that we breathe. About 2/3 of all of our oxygen is produced by organisms that live in the ocean. Transparency is affected by things that are floating in the ocean, or what we call particulates and dissolved material. And this can even be microscopic organisms like phytoplankton, zooplankton, and bacteria. We use something called a Secchi disk to measure the transparency in the ocean. Essentially, it's a black and white disk that you see here on a line that has length graduations, and you just lower it in the water until you can't see the disk anymore and measure how long that is, and that's your transparency. Now, visible light is not all equal. There's certain wavelengths of visible light that are much more important than others, especially for photosynthesis. The most important wavelengths for photosynthesis are violet, blue, and red. And you can see that they have different abilities to penetrate the water. Violet and blue tend to penetrate deepest, and this is basically what limits where photosynthetic organisms can live in the ocean. So usually beyond about 200 to 300 feet, we don't get a lot of photosynthetic organisms. Interestingly, even though red is an important wavelength of light for photosynthesis, it does not penetrate very deep in the ocean. This is why if you're a scuba diver, or if you've ever been deep free diving, when you go down, even just a couple feet, like 30 feet or so, you'll see things start to go from their full spectrum of color to looking mostly blue or green. So here's an example. I think I was at about 60 feet here, and this is what coral looks like in a dive 60 feet down without a flash. Here's what it looks like with a flash. Mostly green and blues because that's the light wavelengths that are penetrating, compared to my flash, which actually highlights what their colors really are. Pressure is very important in the ocean. Water being so dense means that it's heavy. And so the pressure is just the measurement of the weight of the medium surrounding an organism. Air is not very heavy, and so it doesn't feel like a lot of pressure. Water, on the other hand, is much more dense than air. And an ATM is what's called an atmosphere, okay? So at sea level, we're at 1 atmosphere. In the water, every 10 meters, or about 33 feet, we increase by 1 atmosphere. This can also affect the amount of gases in the ocean, because as there's more pressure in the deep water, gases can tend to compress. And so here's a great graphic to illustrate that. Here's a diver with a balloon on the surface of the ocean. 1 atmosphere, 1 bar, 14 pounds per square inch. They're going down 1 atmosphere. So now we're at 2 atmospheres, 2 bars, or about 30 pounds per square inch. And you can see the air in the balloon is condensing. Go down to 5 atmospheres and there's 73 pounds per square inch of pressure surrounding the diver and the balloon continues to shrink. Go down to about 9 atmospheres, which is around 260 feet, and you have 132 pounds per square inch of pressure all over your body. Humans would implode, so that's why he's wearing a metal suit. This is also exemplified by styrofoam. Styrofoam's made basically of air and plastic, and you can see this is before it went down to depth, and this is after. It went down about 8,900 feet, or 1.7 miles, and here's what it condensed to afterwards. This can have huge effects on fishes that traverse deep and shallow waters. Many fish have neutral buoyancy because they have swim bladders. They have this organ inside of them that they can put air into or take air out of, i.e. dissolved gases from their blood, to ensure neutral buoyancy. When they're at depth and you're fishing and you pull them up too quickly, they can't regulate the air in their swim bladder enough because it's condensed at depth. When they come up real fast, it expands and pushes their stomach out their mouth. So this is really bad for fish. Now let's talk about ocean circulation patterns, waves, and tides. Circulation patterns, ocean currents, deep ocean currents, this is so influential, not just for our climate, but also for how nutrients cycle around the ocean. Oxygen is circulated throughout the deep and shallow oceans, and how water moves. It also has profound effects for the distribution of different organisms. So the circulation of the ocean comes from 2 things. The first is winds. Winds drive surface ocean currents. Winds are essentially created by the heating and cooling of air masses. Now remember, hot air rises, cool air sinks. This movement creates winds. A second thing that influences circulation is the fact that our Earth is rotating. Because the Earth is rotating, that means that the air is moving differently at the poles compared to the equator. And this also influences water movement. This difference in movement is what we call the Coriolis effect. And I highly recommend that you watch the videos on the Coriolis effect in the week module. Because the Earth rotates on its axes, winds that are high up by the poles and are coming down towards the equator actually are moving with less velocity. And so they seem to be deflected in a in a clockwise pattern in the northern hemisphere and in a counterclockwise pattern in the southern hemisphere. So before we get into the Coriolis effect, let's briefly talk about how wind is formed. There's a great video talking about how wind is formed, but I'll do a very brief explanation here. Essentially, rising hot air from the equator cools and sinks as it heads towards the poles. The cycle repeats and air returns from the poles back down, and this is what creates wind patterns like our trade winds, the westerlies, and the easterlies. Of these three major wind patterns, the trade winds are the most consistent. The trade winds are essentially air coming down from the poles, warming up, and because they are traveling at less velocity at the poles because of the circumference of the Earth and the rotation of it on its axes, they deflect clockwise. And so this is why our trade winds consistently come from the northeast. We get east-northeast trade winds, very consistent. Again, look at the Null School video. Check this out. It's not a video, it's actually a website of our living planet, and it can show these wind patterns. So our northeast trades are super consistent as air is coming back down. And then as you go up away from the equator, you see the westerlies and the polar easterlies. But these tend to be a little more seasonal than our trade winds. So winds blow across the ocean and move it as well. So the wind can push the surface of the water, and that friction can cause water below to move as well. So you get these kind of like sections of water that are pushing other water, moving deeper and deeper as you go. But because there's friction, there's some energy that's lost, and so the water tends to move in these sections and creates spirals called Ekman spirals. And this is because of the Coriolis effect. The surface waters are deflected such that the net movement of water is about 90 degrees from the direction of the wind. And that's what we call Ekman transport. And so overall, water currents are deflected at a 90-degree angle from the wind direction. And so that's the most important thing you need to remember. So if the wind is blowing in one direction, you'll see the surface of the water moves a different direction because it's got less velocity and because the Earth is spinning. And so it's going to change. And then the column underneath that and underneath that, this is an Ekman spiral. This is the Ekman transport, the net transport of a 90-degree angle. And this is what drives our surface currents, these gyres that I spoke of. So not only does the different waters help push these surface currents around, warm water moving and then cooling and sinking, coming back down, warming, cooling and sinking, etc. But there's also the winds that move this pattern and the Coriolis effect. And so this also brings us to warm currents like equatorial currents and cold currents like the California current. Warm currents like the Gulf Stream, which has profound effects on the climate, the coastal climates of the eastern North American continent and over here in Europe, and also moves around a lot of different organisms and moves around a lot of heat. And these currents also in the summertime help fuel the hurricane seasons. Add on top of that the fact that as you go deeper, density of the seawater increases. You get these different layers. So you get surface layers mixed by wind currents, an intermediate layer that tends to be stable, and then a super stable, uniform, cold, deep layer.